Thank you for coming back from the coffee break. Now we're going to continue with the second lecture, now by DominikInauen.
Thanks a lot. So before I begin, let me thank Carlos and Sari and also Laura for setting up this very nice meeting, and thank all of you guys for coming around and listening to the two of us to explore these ideas with you. So what I want to do in my couple of lectures is to give you, or to focus on the third example Govind was mentioning in the lecture before, which would be the isometric embedding problems for Riemannian manifolds. So this will be the isometric embedding problem for Riemannian manifolds. Let me not write this. And okay, there will be sort of overlaps with what Govind has said before, or is going to say in the next couple of lectures. But it's a nice way of zooming in a certain on certain points, and maybe give a slightly different explanation, and maybe also make some things more precise or less precise. And okay, I'm an analyst, and most of what I will be talking about will be analytic, but I think it's a nice combination of what Govind is going to present, and what I will be trying to present, like a combination of probability and analysis, which hopefully leads to a nice general understanding of these type of problems, like the isometric embedding problems, the theorems by Nash, and what we did with them. So today I wanted to give you, or once again, state the problem. It was stated before by Govind, but let me do it again and maybe focus on some different things. And after stating the problem, I want to give you a rundown of the most classical results about this very classical problem, and mention like the main breakthrough result by Nash, the Nash-Kuiper isometric embedding theorem. And then, so in the next couple of lectures today, I want to give you heuristics about the proof of this theorem. And okay, let me postpone the plan of the next lectures to maybe in an hour, when we have an overview of the problem and what the interesting questions are, which you can ask. And then I can tell you a bit more about what I was planning to show you this week. So the statement of the problem is the following. And okay, please always interrupt me if I'm not making sense, if I'm too fast, or if I'm writing not large enough. Is it fine for the guys in the background? Okay. So the problem is given this abstract Riemannian manifold. So it's a smooth n-dimensional Riemannian manifold. M is just a differentiable manifold of dimension n. And G is this Riemannian metric. So this is a smooth Riemannian manifold. G is this extra piece of information on your differential manifold, which allows you to do geometry basically on the manifold. So it's an abstract piece of information which allows you to define basic geometric, basic notions in geometry, like the length of a curve or the angle between two tangent vectors. So this is what this tensor G is doing. This is an abstract object, and we want to find the realization of it as a submanifold of Euclidean space. And as Govind was saying, the dimension of this Euclidean space, where we want to find the realization of this abstract object, is kind of a parameter. So let me put it into the problem. So given this abstract Riemannian manifold, does there exist a dimension Q and an embedding from M into RQ, embedding, such that, so which preserves distances or lengths rather. So before we were trying to embed graphs graphs or discrete metric spaces preserving distances. Now I want to focus on or point to this small subtlety that we want to preserve lengths, the sense of the following, namely, if I look at the curve on the manifold, using this additional piece of information G, I can say what the length of this curve is. Any length on M, using U, I have a curve in Euclidean space. I can compute the length of this curve in Euclidean space, just as a curve in Euclidean space. And what I want is that these two lengths agree. So such that the length of any curve, gamma, on the manifold, and I measure this length with respect to this intrinsic metric G, is the same as the length of the image curve, U of gamma. And this I measure with respect to the Euclidean metric E. This is the Euclidean metric. In RQ. And I want these lengths to agree for every curve gamma C1 curve. Yellow. Yeah, there's no, yeah. It's equivalent. So this is the Euclidean metric on RQ. So I was just going to say or mention this as an exercise. So what Govind wrote down before was saying, okay, I want to find the U such that dut du is on the flat 2 torus, it was the identity, but you could also just put a general metric G on there. So induced metric is the same as the intrinsic metric. This condition on the length is equivalent to this condition if you're regular enough. So if G is continuous, if U C1. So I'll show that this condition, which is a bit tedious to check. So if you want to find such a map, an isometric embedding, you have to check, you have to take any curve on the manifold, compute the length of the image curve C, if these two agree. So this is very tedious to check, but exactly this exercise showed that if G, the Riemannian metric, is continuous, and okay, by definition my embedding is a C1 map, then this star is equivalent to the following condition, star star, namely that the inner product of any two tangent vectors x, y with respect to G is the same as the Euclidean inner product of these two vectors, du of x, du of y, for every two tangent vectors x and y. And let me just draw a picture of this condition. So here you're on a manifold M. You pick a point, you look at the tangent space to the manifold at this point, TPM. And what I'm saying is that, okay, I have two vectors, x and y. And the intrinsic metric G allows me to associate to these two vectors an inner product. It's just a number. It's called GXY. Now, if I have an embedding, U, which goes from the manifold into Euclidean space RQ. So here I'm in I have the image U of M. I have U of P over here. I can look at the tangent space T at this point, U of P, to the submanifold U of M. Simply look at the images of these two tangent vectors. And okay, a tangent vector, the image through an embedding is just given by the differential. So du of M and what I'm asking in condition 2 star over here is just that the Euclidean inner product, this inner product in R Q. So what I'm asking in this condition is that as soon as I have two arbitrary tangent vectors, look at the images, take the Euclidean inner product between these two vectors in RQ. This gives me a number. This number should be the same as the intrinsic inner product. And it's an exercise to check that this is equivalent to this condition over here, that as soon as you take a curve on a manifold, you compute the length with the help of this metric G, and you compute the length of the image, they should agree. Okay? So this this map, which takes two tangent vectors x and y and associates this number, the inner product, the Euclidean inner product of the image two, this is the induced metric. So this in coordinates, this is just this metric over here. So let me write this down. So the map let me not spend too much time. X, y goes to the inner product of du of x, du of y is called induced, or the pullback metric of u of the Euclidean metric let me call this E through u. So the pullback written U sharp E, sometimes U star. Okay, and let me define definition one. Or first, let's say we are all on the same page. An embedding. Let me just recall this. Recall a C1 map or an embedding is a C1 map such that first of all, it doesn't collapse any tangent spaces. So what I want is that the differential of this map has full rank at every point. So du of P is a full rank for any P. So this is called an immersion. An immersion which is 1-1 is an embedding. U injective. Okay, so let me define what we're looking for in this problem is an isometric embedding. So an embedding which satisfies either star or 2 star. So definition, an embedding, let me call this 1-1, an embedding or immersion is called, so U of mg into RQ is called isometric. If the induced metric agrees with G, so EA2 star holds. To start this condition over here. So as Erwin was saying, somehow we're given this abstract object, this abstract Riemannian manifold. We want to find the realization, and these are actually also the terms Weil used in 1916. So he was saying this abstract Riemannian manifold is like the idea, whereas the embedded manifold is the realization or the reality. And the question over here is the idea the same as the reality? Can I realize every idea? And so to realize every idea, we have to find an embedding which is isometric. And to find this, we have to find an embedding which satisfies this condition over here. So satisfying this condition, you can see the condition is bilinear in x and y. So it suffices to check it on a basis of the tangent plane. If I pick a point and I take a basis of the tangent plane and I check this condition on the basis, what I end up with is a system of PDEs, but it's a finite system of PDEs. And so this is the system we want to solve if we want to find an isometric embedding. So in local coordinates, around some point P, we can write the metric G as some coefficients, Gij, so it's a matrix of coefficients, and then dxi, dxj. So Gij are simply the coefficients of this metric tensor in these local coordinates xi. And you can think about the metric as simply a matrix, n by n matrix. And here I'm using Einstein summation convention. So whenever I see an index which is repeated once in the bottom and once in the top, it means that I'm summing over this index. So this is actually a sum over I and j from 1 to n. Okay? And then U star then reads, or U is isometric if and only if this system of PDE holds, relating the coefficients of this metric, Gij, and the partial derivatives of U. So you see the derivatives over here, du in the direction dxi. And so this is the same as the inner product between diu and dju. And let me write this out for once. So it means I'm summing over all to q of u, and I'm taking the partial derivative duk dxi duk ddxj. And this is a system for I and j between 1 and n. And let me call this system I. So this is the system. Sorry about patient. So a good question. So usually,
sorry, I said that why is the Q not being allowed to reach n? It's
so very good question. This is just, I mean, I could put Qn over there, but the chance that a Riemannian manifold of dimension n has an isometric embedding into Rn is very small. So the chance is that, I mean, the manifold over here, if it has an isometric embedding into Rn, it has to be flat. So you only get very little freedom in G. But you could take n over here, and okay, for most G, you have no chance of having Q equals n. But thanks for the question. Okay. So I started with this problem, find the realization of any Riemannian manifold. A realization such, I mean, respecting the geometry of this abstract object. And I came to a system, finite system of PDEs relating coefficients of G and first derivatives of U. And it doesn't look too bad, this system. And note, simply counting, of how many equations are there? Well, both sides of this equation are symmetric. N times n plus 1 divided by 2 equations. And I will give this number a special notation. So I call this n star. The dimension of the space of symmetric matrices of size of n times n matrices. Of n nonlinear PDEs, nonlinear PDEs. In how many unknowns? Well, we have exactly Q unknowns, the coefficients of this map U, which is going into RQ. Unknowns. And I said, okay, this number Q over there is kind of a free parameter. Does there exist a Q and an embedding into RQ? And now simply from looking to the system of equation we get, which is the system describing this conservation of length, the natural Q seems to be exactly this one. The number of free parameters should somehow equal the number of equations. So in Q is free, but Q equals n star seems natural. Okay. Any questions to this point? Okay, very good. So that's the problem. Find a solution, and as Govin said, a reasonably smooth solution to the system of PDEs. Just looking at this system, reasonably smooth, you might think, okay, C1, it's a classical solution. So you can take derivatives, it's a nice embedding. The metric agrees with the intrinsic metric. So let me tell you about classical results over here. Take this one. So 1, 2. That is. Maybe afterwards. Classical results. So, as I said, this system I doesn't look too bad. It's just G equals duct. It's a quadratic nonlinearity, but doesn't look too bad, first order. And the natural space in which to try to find solutions is where Q equals the number of equations. So this was exactly the conjecture which was put forward. This doesn't go up. by Schläfli in 1873 already. So conjecture Swiss mathematician in 1873. And he looked at the system and thought exactly the same, namely, if Q is n star, there should at least exist local solutions to the system. There exist local solutions to I. Local solutions means around any point of the manifold, I should find a small neighborhood such that, and an embedding from this small neighborhood into our Q such that this system is satisfied in this neighborhood. And okay, Schläfli was thinking about the analytic category. So he was thinking analytic metric, find an analytic solution. So, and it turns out, can you read over here? Or right here? So it turns out that this is true if the metric is analytic, if G is analytic. And you get an analytic local solution. Around any point, you find a small neighborhood and an analytic isometric embedding. This was proven by Janet in a two-dimensional case, 1926, which was, okay, Burstein had in 1931, any dimensional case. This is basically a variant of the Cauchy-Kovalevskaya theorem. So extension of, solving analytically like a Dirichlet problem. So this is Cauchy-Kovalevskaya, and then you had Cartan in 1927 with a very geometric proof method of the moving frames. Okay, analytic category, you're fine. General case, if you're smooth, just one step down. Okay, the goal is find, show that if you have a smooth metric, around any point there is a small neighborhood and a smooth isometric embedding from this neighborhood into R n star. This is still widely open. Even the two-dimensional case. Okay, so first, bad results. Nicely, equation doesn't look too bad. This is a natural space to find solutions. Even the local problem seems to be difficult. I should say for completeness, the difficult part is getting down to this codimension. So if you allow for a bit more flexibility, a bit more unknowns, this result is actually true. This was proven by Gromov. So true, oh, red is not good. So true for Q equals n star plus n. This is Gromov-Roeckl. Gromov-Roeckl in 74. The difficulty is really going down to n star. Okay, so this first bad results. And now let me give you some more bad results. Notice that this natural dimension n star, if n is equal to 2, this is 3. So 2 times 3 divided by 2 is just 3. So in the two-dimensional case, the natural space of solutions, or the natural Euclidean space to embed two-dimensional manifolds is just R3. So more bad results. So what Hilbert proved in 1906 is that there exists no solution. So going from the local problem, which was considered by Schläfli, to, okay, we want to find a global isometric embedding. We want to find a global solution, like embedding the whole manifold. For H2, you cannot find an isometric embedding into R3. C2. So hyperbolic two-phase, you cannot embed in a C2 way into R3. This was proven by Hilbert in 1906, I think. He proved more generally any manifold with constant negative curvature you cannot put into R3. So two-dimensional manifold with constant negative curvature, you cannot put it into R3 by a solution which is C2. Solution of this equation over there, which is additionally C2. So this is negative curvature. You also have bad results for zero curvature. So this is, there doesn't exist. That's nice that Govind mentioned the two torus. If you want to put the flat two torus, exactly the example Govind was mentioning, flat two torus, if you want to put it into R3 in a length preserving way, you cannot do it with a C2 map. Isometric embedding. And this was Eisenhardt in 5. So this is a negative curvature, zero curvature. If you have positive curvature, the situation is a bit better. And so this was considered by Weil. So positive curvature. Is a bit better. So Weil considered in 1916 was the Weil problem. This was Hermann Weil in 19. So he was looking or interested in this very specific situation where your manifold is just a sphere and you have a metric on it which has positive Gaussian curvature. It's like a convex body. And what he wanted to show is that any metric on S2 with positive Gaussian curvature, you can realize it as some nice convex surface in R3. So show that any metric G on S2 with positive Gaussian curvature, Kg bigger than 0, can be uniquely realized as a convex surface in R3. So in more modern terms, show that in the special situation where mg, can you read this? Yeah. So in the special situation where your manifold is S2, two-dimensional manifold, closed, nice. Your manifold, your metric on it is a nice metric with positive Gaussian curvature. Show that there exists a solution, global solution to the system of PDEs, and it's unique. Now, unique, we're trying to find maps, embeddings, which preserve the length of curves. And of course, if I have one such map, I can simply move it around, and it still will be length preserving. I can simply rotate it, still length preserving. So unique, or uniquely over here, is always meant modulo these isometries of RQ or R3. So I can always compose this map with such a rotation, with a translation. I will get another map. But for us, this is the same map. So uniqueness is modulo rigid motions. So EA, isometries of R3. Okay, so let me come back to it. We want to find isometric embeddings. Any Riemannian manifold we want to somehow embed into some Euclidean space. We saw that the number of equations is n star. We deduced that the natural space to look for solutions is when Q is exactly this number of unknowns equals number of equations. We saw that local problem had problems. We saw that also the global question, there are problems if you're after C2 solutions. Okay, in the case where negative curvature, zero curvature, positive curvature, where we ended up with the Weil problem. And in fact, this problem has a solution. So in the 50s, this problem was completely solved. And in fact, we have the following two theorems. The first is an existence theorem that, yes, in the special case, you can always find an isometric embedding. Yeah.
Hold on. That's good. The bad news results are just globally. They are locally neither globally or locally.
Global.
Only globalists prove that it doesn't hold. And what is wrong with the what goes wrong for proving non-existence?
What goes wrong over here?
Yeah, because you can, for smooth, you can prove it, right? Because of the conjecture that you have by well, I don't know how to pronounce it.
Schleifli?
Yes.
But this is just a conjecture. So it's only true if it's analytic. General case is open if you're smooth.
Okay.
It's true if you if you increase the dimension Q over here.
Okay.
So these results over here are always, I mean, N is 2 and Q is 2 star.
Yeah.
3.
And but how could you prove something? I mean, something goes wrong somehow. How would you prove a non-existent result for this?
Very good question. So the first one is, let me focus on this one because it's a bit easier to explain. So the point over here is that this is a compact or closed manifold. It has zero curvature. So I'm taking the flat torus. This has no curve. I mean, it's a flat. Any curve which I look at in there, it's a flat curve. It doesn't bend, or it has no Gaussian curvature. So if I'm thinking about an embedding, which is C2 into R3, it has to be a nice compact surface, because I have a compact domain over here. It has to be closed. And now, so I can imagine the picture, any embedding of T2 would look something like this. And I'm assuming it's isometric. Now what I can do is look at a sphere which touches, like say 0 is here. I move my manifold such that 0 is here. And I look at the farthest point which is away from 0. Then I see that my whole manifold over here is contained in a ball with this radius. And what I see over here is that I have a point which has curvature which is bigger than the curvature of this sphere at this point. And this is strictly positive. Right? On the I have my shape, so this is U of T2. This is some ball BR. It touches in this point. So I see that in this point U of P, my surface, so this submanifold U of T2, it has to bend more than the sphere because it's really enclosed. So at this point, somehow the surface of this submanifold, it has a curvature which is greater than the curvature of this sphere, strictly positive. And because I'm C2, Gauss tells me that in fact curvature is an intrinsic property. So I can compute the Gaussian curvature of this submanifold simply by looking at the intrinsic metric. So Gauss tells me if my embedding is C2, theorema egregium, Gaussian curvature is an intrinsic property. In fact, it was extrinsically defined, but then Gauss realized that, in fact, this is an intrinsic property. And because T2 is flat, the Gaussian curvature is 0, has to be 0 everywhere. If I have a C2 map, the intrinsic curvature is speaking to the extrinsic curvature, and this gives me this contradiction.
And that sort of contradiction, sorry to keep bothering you, but that sort of contradiction, you wouldn't find it if you compare to manifolds which have sort of flexibility of having negative curvature. Let's say that you compare an H2 against another manifold with negative curvature. Maybe if you consider the case in which M is something with negative curvature, but instead of putting the U into RD, you can perhaps put the U to an IHD or HQ, sorry, or something like that. So if you don't want something as simple as RQ, because it cannot hold the negative curvature part, maybe you can put a simple example which still has negative curvature, but it's at the same time a little bit simple.
Can you repeat the question?
U goes from difficult to simple.
Yeah, into a Euclidean space, simple.
So you can, RQ is, let's say, simple, is easy to handle. So maybe if it is slightly more difficult to handle, but still simple, I mean, still not so difficult, maybe you can pose the question of whether you can put U, whether you can put MN isometrically into something a little bit more complicated than RQ, which could perhaps avoid this little thingy.
Absolutely, yeah. I mean, if you change the ambient manifold, then this argument might break down.
You might, okay. Thank you.
Thanks. Okay. So, okay, the while problem. So as I said, completely solved in the 50s, let's say, because we have the following two theorem, theorem 1 or theorem number 1, 2 maybe. So this is existence in the while problem. Namely, if your metric is C2, then there exists U isometric. U isometric. And this was proven by a number of people. For the sake of time, I'm just going to write them in the notes and maybe tell you. So this was proved by a class or very PDE type approach, actually an approach which was proposed by Weil, which has now become the continuity method in PDE. So this was worked on so Levy actually solved the analytic case. Then you had Nierenberg in his PhD thesis. He showed that this is true if G is in C4. And this is due to Heinz, the C2 version. This is PDE approach, and then there was a very geometric approach led by Alexandrov, and he somehow found a generalized solution U to this problem. And it wasn't known whether this generalized solution had the right regularity to be actually considered a solution of the problem. This was then proven by Pogorelov in the 40s. So the second theorem over here is the uniqueness part, and this is actually why I'm telling you this. So this is uniqueness or rigidity. So what it's telling you is that if U is an isometric embedding which is C2, so always in the while problem. So S2G with positive Gaussian curvature, isometric embedding into R3, iso embedding, then U unique. Up to rigid motion. So if anybody gives you two isometric embeddings which are of class C2. They have to be the same one up to rotation and translation. They have to be congruent. And this was proven by Kohn-Vossen in 1927 analytic case. Yeah, okay, this is due to Herglotz, the C2 version. So this was done in the 50s. So known the 50s. And this was the state of the art in the 50s concerning, so roughly speaking, concerning the question of, concerning this problem. Can you always find an isometric embedding? And okay, so bad things happen if you're a negative curvature, zero curvature. There were these examples. Positive curvature, you find a unique solution, as you would hope from a determined problem. So, but then Nash came along, and he actually showed us that the situation is much different. So, but then, and let me state this as a corollary. So corollary 1.4. This is Nash in 54. And he showed us that the situation is actually much different, namely, you can always find solutions. Any G you give me, you always find a map, which is an embedding preserving the lengths, into some Euclidean space. And moreover, you always find solutions, and often, even when we didn't expect any. So what he showed is not only you can find solutions, but you can find plenty of solutions. There always exist plenty of solutions to your system, I. And sometimes even when the codimension or when the dimension Q is less or much less than dimension when the number of unknowns is much less than the number of equations. And okay, Nash's theorem is actually more striking than this corollary over here. So to state it, I have to first wipe the board and then tell you what a short map is. The short map is basically what Govind introduced before. It's something which is, he called it a sub-solution, I think. Relaxation. So, over there. This one. Relaxation. Let me go with a fancy chalk. So 1.3 would be the Nash-Kuiper theorem. So what Nash says is, if you give me a relaxation of an isometric embedding, which is just a map which shrinks all the lengths. So an immersion, and he calls this short. U from M is called short, and maybe strictly short. Strictly short. If it shrinks lengths of curves, if the length of any curve gamma is bigger than or equal to the length of the image curve, for any gamma C1 curve, and strictly short, of course, I have a strict inequality. equivalently, on the level of the metric tensors, this is when G is bigger than or equal to induced metric, simply as positive definite tensors. So the difference over there is positive definite. That's quadratic forms. Okay. And Nash's theorem is then the following. So Nash in 54. You give me your manifold, let M n, and for the purposes of these lecture series, let me take it compact. Nash doesn't need a compact manifold, but this is simply a smooth n-dimensional compact manifold. And G is a continuous Riemannian metric on M. Continuous Riemannian on M. And what Nash says is that if the codimension is at least 2, so if Q is bigger than or equal to n plus 2, you just give me 2 degrees of freedom more than n, but okay. Then, and you give me in addition one of these maps, which is which shrinks lengths. So you give me a map into some Euclidean space of codimension at least 2, which shrinks all the lengths. Then what I can do is in any small neighborhood around this map, I can find a map which is length preserving. So any small neighborhood, if Q is bigger than or equal to n plus 2, and U is a short immersion or embedding / embedding. Then for any epsilon, so in any small neighborhood, for any epsilon bigger than 0, there exists an isometric map. So it's a solution of your system of PDEs of regularity C1, very classical solution. This map is an immersion or an embedding, depending on whether you start off with an immersion or you start off with an embedding. And it's arbitrarily close to the short map. Immersion / embedding. Such that, well, it's a solution. So G is induced metric of V. It's isometric, preserves the lengths. And in addition, it's a short map. Is everybody familiar with this? I mean, that's right. This is the supremum x in M of, or P in M of U of P minus V of P. And then this is the Euclidean norm. This is less than epsilon. So it's quite strange, because you could give me a map U, which is short, but it's very short. So it shrinks all the lengths a lot. Still, in a very small neighborhood of this map, I find a map which is length preserving. And so when this theorem first came out, it was super surprising. And okay, first, it's called the Kuiper theorem today because of the contributions of Nicolas Kuiper. So theorem 1.7 is due to Nicolas Kuiper 1 year later. I mean, Nash said that this should be possible in his paper. He didn't provide a proof. This was then done by Nicolas Kuiper. He showed that actually this codimension restriction 2 can be lowered to 1. So Q bigger than m plus 2 is fine. In theorem 1.6. Okay. So this, in particular, you can have a two-dimensional manifold isometrically embedded into R3 if you have a map which shrinks the length into R3. So this theorem was super surprising, and I want to give you a few reasons why it was surprising. So first of all, let me drink one sip of water, check the time. Wow. So first of all, it's a conditional theorem. Nash says, if you give me a short map, I give you an isometric map. But these short maps, they're really easy to produce if the manifold is compact. You simply take any embedding and you shrink it. And a differentiable embedding you can always find by Whitney, for example. Maybe you already have one. Maybe you're starting out with a manifold which already lives in R3 or in some Euclidean space. Put some weird metric on it, you just shrink it, you get a short map. So note, if manifold is compact and U into RQ is any embedding, or any immersion, so differential immersion, nothing with respect to geometry, then epsilon U is short for epsilon small enough. So basically Nash tells you, if you have a map which topologically puts M into some Euclidean space, you can find a map which also solves this differential equation with concerning geometry. So the only obstructions for solutions to this system are actually of topological nature. If there are no topological obstructions, you can also find solutions to this system, which is a system about geometry, about lengths of curves. So corollary 1.8 is if there exist topological embeddings, then there also exists isometric. Immersion or embedding. Which is kind of strange because somehow this additional, we've worked so hard to somehow guarantee this condition over here. And now Nash telling you that you can forget about G. Just look at, can you put this manifold topologically into some RQ, if it's compact, shrink it, you find a solution of this system. Okay, so one surprising reason over there. Moreover, the second reason why it's so surprising is because of this one over here. So it seems that around any short map, in any small neighborhood, you can find a map which is length preserving. So the set of solutions to this system of PDEs over here is somehow dense, P0, dense, in the set of sub-solutions, the set of solutions which are short. Moreover, let me take a different. And this is what we call the flexibility of isometric embeddings. Moreover, the set of isometric maps is somehow C0 dense in the set of short maps. And in PDE terms, this is set of solutions. This is set of relaxed solutions or sub-solutions. So you're not solving the PDE, but you're solving an inequality over there. So short maps simply solve the equation in an equality sense, whereas isometric maps, they solve it in the equality sense. And this is what we call the flexibility. Of isometric embeddings. And what I want you to note here is that this flexibility, it's not so surprising if Q is super large. If you have a lot of freedom, if you have a lot of unknowns to play with, you might expect to have a huge set of solutions. But Nash tells you that, okay, Q only, or Nash and Kuiper tell you that Q only has to be of the order of n. So, okay, Nash, Kuiper, and Whitney. Whitney tells you that you always find a topological or a differential embedding into R2n, which is of the order of n. So you find, so Q has to be of the order of n, whereas we have of the order of n squared equations. Q is very large, you have many more equations than unknowns. And still you have this kind of non-uniqueness over here. Still you have this flexibility. And this was a very surprising instance of this nowadays a bit more well-known fact. And it turns out that this flexibility over here is not due to the underdeterminedness of the PDE, the amount of freedom, but due to the low regularity which you get. So the flexibility is somehow reflecting, or is the reason you have this flexibility is this low regularity over here, C1. Even though C1 looks like a perfect regularity for a solution of the system. One, 4. Yeah. So there always exists plenty of solutions. You can always build short maps. And around any short map, in any small neighborhood around it, you find an isometric map. So, okay. And sometimes even when Q is less than n star. So, okay, if n star, or if n is 2, n star is 3, you cannot hope to be better than this number. But usually, I mean, you always find solutions into 2n, embeddings into 2n, immersions into 2n minus 1 of compact manifolds. And usually this is much smaller than n star. So this is what I meant there. So just let me write this down. Note for Q equals n plus 1 and n bigger than or equal to 3, the system I is heavily overdetermined. Still have flexibility. Which is surprising. Some more reasons. Why is it surprising? Flat torus into R3. I can simply take the usual flat torus, or the usual torus picture over here. I shrink it. It's a short map of the flat torus. I mean, I glue the edges. It's not isometric. I shrink it. It's short. So Nash tells me that there exists an isometric embedding of the 2 torus in R3. Whereas Eisenhardt tells me that in C2 this is not possible. Moreover, note the following contrast. So there exists U flat 2 torus into R3 C1 isometric embedding. There exists an isometric embedding of the hyperbolic 2 space into R3 C1. C2, no. 1, yes. This one even, this one is not compact, but okay, you can make it compact or approximate it to be compact. But just note no existence in C2, existence in C1 with surprising amount of stability. It also seems to, so this theorem over here, Nash-Kuiper, seems to contradict the rigidity in the Weil problem. Why? Well, sorry. The rigidity in the Weil problem told you that if you have a C2 embedding, it's unique. But now let's simply take this simple example. Moreover, Nash-Kuiper theorem seems to contradict corollary 1.5, as theorem 1.3. The rigidity in the Weil problem. Namely, just look at the standard 2 sphere with the round metric on it. Round metric. So just the 2 sphere sitting in R3. This is my manifold, this is my metric G. The Weil problem tells me, okay, this is the metric with positive Gaussian curvature. Weil problem tells me that the only isometric embedding of this guy into R3 is just the standard inclusion, or translated, rotated. You cannot deform this guy in an isometric way other than simply moving it in C2. Nash-Kuiper theorem tells me, well, okay, I simply take the inclusion, I shrink it with epsilon, its short map. Then in any small neighborhood around it, take any small epsilon, I find a map which is isometric. So you can put this standard sphere of size 1 into any small ball of size epsilon, length preserving. So standard 2 sphere. Then U, which is epsilon halves, and then for any epsilon in 0, 1, say, epsilon halves the inclusion is short. So the Nash-Kuiper theorem tells me I have a short map in any small neighborhood of this short map. I find a map which is length preserving. So there exists V C2 of this manifold into R3 C1 iso embedding such that the image is contained in the ball with radius epsilon. And it's C1. Fortunately, we don't have the projector over here, but there are very nice images, luckily for us. So a team of French mathematicians around Vincent Borelli, they managed to get images of what such an embedding over here would look like. And you can imagine it has to be very crumpled because you only have a very small amount of space, but still you have to travel these distances of order 1. And so how you do this is by roughening up the surface of the sphere so that a small creature on this manifold over here has to travel far and far because it has to go down all these small ridges and valleys. So Google the or Google reduced sphere. Reduced sphere. EVA project. So Nash-Kuiper tells you that you can crumple this. The rigidity theorem of the Weil problem is that you cannot do this in C2. So this is C1. And so theorem 1.13 implies that the only iso embedding B, which is C2 of this manifold into R3, is the inclusion. Standard inclusion. So you can see a very drastic difference in behavior of solutions of my system of PDEs depending on their regularity. And note that both regularities are completely fine. C1 is a nice classical solution to the system of PDEs. But you see, and this would be the first instance of this fact where you could see this, that solutions of nonlinear PDEs be like below a certain regularity threshold, they behave unpredictably. Like in C2, you have a nice unique solution in this case. And then somewhere, if you pass to C1, you have complete flexibility. And somehow it's a first instance where this regularity, it's not just a byproduct of the proof or so, but it's really a requirement. Depending on which regularity your solution, which regularity your solution has, it might behave completely different. So this was this first instance of this nowadays a bit more well-known fact. Below certain regularity threshold, solutions with linear PDEs might lose their predictability. And I want to talk about this a bit more now because of time reasons, probably only the day after tomorrow. So it's, of course, a very natural question to ask, what happens in between? You have complete uniqueness in C2, you have flexibility in C1. Is there something in between which distinguishes between these completely contrasting behavior? So do you have, let's say, uniqueness in this case, also for embeddings which are C1 alpha for a large alpha, close to 1? And do you have flexibility also for embeddings which are C1 alpha, alpha small? And what happens in between? Is there a sharp threshold? Is there a gray zone? And so on. And this leads to the threshold problem. So this is the threshold problem, which either tomorrow or Wednesday. I want to talk a bit about this because it's at the core of our investigations, or yeah. Okay, let me just check that. Yeah. Are there any questions at this point? So let me tell you that the plan, or what I planned, but it's flexible. So depending on what you guys like to see, we can also adjust. My plan was the following for the next, next hours. my plan was to show you proof of the Nash-Kuiper theorem minus most of the technical details, but still having some details over there. And I plan to get rid of most of the technical details by just considering an easy setup where I'm not embedding a whole manifold. I'm just embedding the, let's say, n-dimensional disk. I put some metric on it because then, okay, I don't have to worry about charts. I don't have to worry about partition of unity. I just have a map from Rn to Rq, or a subset of Rn. I have a nice metric G on it, and I want to embed this. And the condition over there simply, as Govind was writing it, the condition of being an isometry translates to this matrix identity over here, or matrix field identity. And so, okay, the plan is, well, first proof of Nash-Kuiper theorem, or more, just again, throwing away one technical detail. Let's just stick to the case which Nash considered of theorem 1.6 minus technical details. Then talk a bit about the threshold problem. So this means, is there flexibility? Or what about E1 alpha isometric embeddings? In terms of flexibility and rigidity. And then, okay, there are variants of this threshold problem, which I might want to mention. I think that that's my, okay, it doesn't look like much of a plan, but that's my plan right now. The plan has sub-steps, and I will go into these sub-steps when we get to 1 and 2. So maybe for today, I think I still have, what do I have, 10 more minutes? So I have 10 more minutes. Maybe let me take, again? 7. Also.
So yes, 6:15, we finished.
I will started late.
Ah, yes.
Started late. But okay, I can. So my plan for the remaining time today was to give you somehow the heuristic of the proof, which somehow, or what the ingredients for the proof over here are. And then this should set up something which Nash Govind is going to talk about tomorrow. And then we go into the details of the proof tomorrow. So let me maybe try to do this as quickly as possible. Okay, in this plan, I was roughly trying to spend some amount of time, let's say 3 lectures on this, and 1 lecture on the rigidity. So flexibility and rigidity. But as I said, it's adjustable to whatever you guys feel like. Okay, so proof of the Nash-Kuiper theorem. Where was I? 1.3. Let's do 1.4. Proof of the Nash-Kuiper theorem. And let me give you the setup, which is setup. Now takes out most of the main difficulties, but still keeps the ideas over there. So setup is codimension n+2, as in Nash. So M is just a nice smooth domain Rn. Nice, smooth, compact, or bounded smooth bounded. Where omega in Rn is smooth bounded open. Think the unit wall. So G, your Riemannian metric there, it's just a matrix valued function on omega. So G is simply C infinity from omega bar to the space of symmetric n by n matrix positive definite. Smooth matrix field represents the Riemannian metric. And the goal is, for the theorem we want to prove, given u from omega bar into n plus 2, strictly short, or short and smooth, any epsilon bigger than 0, find V C1 such that, so it's now simply a function from Rn to Rn plus 2, such that it's isometric. So the intrinsic metric G is the same as the induced metric of V, but the induced metric of V now in this coordinate form is simply the product of the transpose of the Jacobian of V, Jacobian matrix times the Jacobian matrix itself at any point on omega bar, and V minus U 0 less than n. So this is the theorem I want to prove to you. And let me give you the heuristics of how Nash managed to do this. I don't think I managed this in 5 minutes. Sorry, Govind, I don't think I managed this in 5 minutes. So then I think I will stop over here and just give you the heuristics tomorrow. But basically, what Nash did, I mean, just teasing a bit, what Nash realized, what Nash realized is, okay, you start with a map U, which is strictly short. All the lengths are short. And now somehow I want to find a map where all the lengths are correct. So somehow I have to stretch out this map U, right? I want to make everything larger. I want to stretch out this map. And what Nash realized is a nice way to find this final map V, which is an isometry, is to stretch out the map U successively. So iteratively, we build a sequence of maps which are short. Let's call these maps UQ. And Q is a number which runs through N. And I want to stretch, so I want to make each map slightly less short than the previous one. But still, I want to converge the end to this metric G over here. So I want to build a sequence of maps UQ, such that UQ plus 1 is less short than UQ, but still short, and such that UQ induced metric converges to G. Okay. Let's now take M, because I usually take Rm. Okay, build a sequence of short maps. Each map is slightly less short than the previous one. In the end, I want to converge to G. And I want that this map, this sequence over here is Cauchy in C1, such that the limit, so so that it has a limit in C1, and this limit is actually an isometry. And now the crucial step is how to go from UM to UM plus 1. So how to stretch out a map while staying arbitrarily close. And Nash realized that a nice way to do this is just by adding spirals. So imagine this is your map U. You want to increase the length along this map U. So here the length between this point here and this point here is just, I can compute it. What I now do is add a spiral. So my new map, let's call it V, is simply spiral around U. And I can tweak the parameters of this spiral such that I stay very close to U, but still now, and this point over here has increased because I have to go along the spiral. I have to go along the spiral, but still I can stay close to U. And so Nash ansatz for this spiral, and he showed that in fact such a spiral, such an ansatz increases lengths, and it does so in a controllable manner, and I can stay close to my map U. And then, okay, there are several ingredients, more than this, and we'll come to this tomorrow. So let me stop over here, and thank you for your attentions. Please, yeah.
Do we have more questions for Dominik? Is that? Yes, there's one.
Thank you very much for your lecture. So I would like, this last heuristics you gave us about the proof, on the proof of Nash's theorem, then we could restate Professor Menon's idea of the previous lecture as thinking that is the solution to diffusion dynamics.
That would be quite interesting to see. Yeah?
So that's exactly the idea I've been trying to channel for like 7 years. Which is why I reduced the graph and I think that's exactly the point. Where you make the sequence. Actually, if you look at the paper, it's very easy. But today we do just control of them. And so I've been trying to get it right. But as you also done before, you have to solve the PDE. And since you have to So let me say everything again. So the idea of sub-solutions over here. So you can see the idea of relaxation. And over here we are making a sequence that's kind of driving us towards, let's say, these extreme points. And so the idea that I began with was exactly, is it possible to randomize the Nash scheme so that one could get a natural diffusion that would drive one from the interior to these. But I've not been able to successfully accomplish that goal. What has become clear in between, and I think actually where Dominik stopped today is a natural point for me to begin tomorrow, by kind of showing you places where probability theory is natural in the problem and provides a complementary view of the analysis. So somehow that's kind of the piece. Yeah, but the idea of the last lecture was really in some sense to make these diffusions and to get them to work. I should also say that please do Google these images that Dominik has shown you so that you can see the striking nature of the solution to these PDEs. But I should also point out that these are the only images that we exist. So these PDEs have been around since these theorems have been around since the 1950s. But in fact, the actual numerical computations, so for many PDEs, such as PDEs of fluid mechanics, we have very good numerical schemes to compute solutions to these PDEs. But in fact, with Nash's proof, it's actually it was really a major achievement by this French group to kind of convert the proof into a numerical scheme. But I feel like we are still very much scratching the surface. So even kind of finding good numerical schemes over here is actually a very interesting and largely open problem.
So let me add on this. So they don't only have pictures for the reduced sphere, but they actually have pictures for this torus and for this hyperbolic space. So this is pretty new, the hyperbolic space. But they have a very nice picture of the reduced hyperbolic space, the reduced torus. This was actually the first one, the torus. This one in between, and the hyperbolic space is the most recent. So they look very nice. They're also, for the torus, there is a 3D printed out model somewhere. Check it out. Yeah, that's the sphere, exactly.
Are there more questions? Good. In this case, let's thank Dominik again.